So hexoses are sugars with 6 carbons. Now, this OSE means it's a sugar. And then what will come in front of the os will tell how many carbons are there. For example, X, pent, tri, hexa, like that. So those determine how many carbons are in that sugar. Now you know the general formula for carbohydrates. In this case, monosaccharides. That is CN, H2N, H2O, N. So since these have got 6 carbons, therefore the general formula is going to be C6H2O6, which you can also write as C6H12O6. Now, if they give you a list of sugars, they want you to determine which one is a carbohydrate. You just need to look at the ratio of carbon, hydrogen, oxygen. The ratio is always in the ratio for hydrogen, first starting with a carbon 1, hydrogen 2, oxygen 1. This is the ratio of carbohydrates, in this case monosaccharides. That should be the ratio. So apart from, of course, we talked about deoxyribose, which has lost 1 oxygen, but in the same way the ratio is 1 to 2 to 1. So if they've given you just formulas, they ask for you to determine which one is the carbohydrate. Make sure that this formula is seen. Now let me just write this. C6, sorry, not A6, C3, H6, O3, and then C3, H8, O3. Which one amongst these is a carbohydrate? Who can give us an answer to that one? Yes, Jacob.
The first one.
Okay, the first one. Good. How did you tell that it is a carbohydrate? Yes, Jacob.
Just like the way you have explained, the ratio is always 1, 1, 2 to 1.
Okay, good. The ratio is 1 to 2 to 1. All right. So you need to take note of that. Okay, now let's go on and look at hexose sugar. So when you're talking about hexose sugars, we've already written their formula C6H12O6. Examples of hexose sugars, the first one, we have glucose. It has got 6 carbons. We have got galactose, and we have got fructose. So you need to know these three examples of hexose sugars. They all have got the same formula. The only different thing is the way their structures are. Remember, we said the formula doesn't tell how atoms are arranged. So the arrangement of atoms is what determines whether it's glucose, galactose, or even fructose. All right. Now, we need to know that hexose sugars are therefore energy sources. So this gets to provide energy. You can think of just glucose. If we eat in shima, just a lot of things, cassava, there's glucose there. So those are there for energy. And these are oxidized during cellular respiration, so to release energy. Now, exo sugars are used in the synthesis of disaccharides. That's another function. Apart from energy source, they are used to make or to synthesize disaccharides. Remember, we are talking about hexose sugars. These are monosaccharides. Monosaccharides are simple sugars. When two monosaccharides or more than one monosaccharide combines are going to form disaccharides. So same with these exo sugars. Actually, it's only these exo sugars that are going to be used in this course that we are going to be considering to form disaccharides. We are going to talk about maltose and these others. They are formed from these monosaccharides that we are talking about now. Okay. So monosaccharides isomers include, one, we have got optical isomers. Apart from optical isomers, we've got also stereoisomers, and then we also have structural isomers. Okay, remember we are saying the general formula of hexose sugars, these monosaccharides, is C6H12O6. Now this formula will not tell us how particles are, I mean how atoms are arranged. So just the arrangement of atoms is what leads to optical isomers, stereoisomers, and structural isomers. Now what do we mean by all these types of isomers? So firstly, when you're talking about structural isomers, we mentioned three examples of hexose sugars: glucose, galactose, and fructose. So glucose and fructose are examples of structural isomers, and these are exam questions. So these two are examples of structural isomers. Why are they structural isomers? They've got the same formula, but the way the atoms are arranged is different. For example, fructose is a ketone, meaning that the functional group for carbohydrates is on the middle, while glucose is an aldehyde. If you have forgotten, we said that the functional group for all carbohydrates is a carbonyl functional group. Carbonyl, that is carbon double bonded to oxygen. So if this functional group is at the end of the chain, we are going to call that as an aldehyde. If it is on the middle of the chain, we are going to call it as a ketone. We are going to look at the structures for glucose, fructose, and galactose. We are going to see what we're talking about. And then we have got also stereoisomers. Now, stereoisomers. Yes, Jacob, there's a question.
So for structural isomers, they have the same chemical formula but different structure formula.
Yes. So,
It's clear now.
all right. So let me just give an example of these same two I've written here. Uh, the same glucose and I mean fructose. So when you consider, let's write glucose here and then fructose there. So we said we can write these formulas for carbohydrates in a simple way by just drawing a line like that. Remember, these have got 6 carbons, and then we are going to have glucose has got the functional group at the end there. Because it is at the end, at every point where you see like there are lines which are meeting, there is a carbon at that point. So at that point there is a carbon, and carbon should always have 4 bonds, but we have got 1, 2, 3 bonds. So we need another bond, and that bond comes from an hydrogen. So I've got an hydrogen there. So I've got the first carbon here, second carbon will be on this middle, third carbon, fourth, fifth, and then the sixth will be at the end. He'll write it as CH2OH. Alright. Now, when you are drawing the structure for glucose, one thing you should know is that it makes more like an S. The OHs, that's how they are. So the first OH, we are going to have an OH here. Another OH is going to be here, but I'll not write it as OH, I'll write it as HO because it is the oxygen which combines with the carbon which is here. And then there will be another OH here, and then another one there. Where I've not put anything, they are hydrogens. So if you want to know that this is because, trust me, glucose and galactose are going to confuse you. This is how you can easily tell. So it will make more like an S where the OHs are going like that. But this S doesn't go like this. It doesn't go up to here. Don't put the OH there. Just like that. So this is glucose. And then when you are talking about fructose, it's more the same like glucose, but the only different thing is that the carbonyl functional group is not at the end. Remember, the same carbonyl functional group, if it is at the end, is called an aldehyde functional group. But in this case, in galactose, the first carbon has got CH2OH, even the last carbon has got CH2OH. The functional group which is the carbon in functional group, is at carbon number 2. So at carbon number 2, you are going to see this. And then the rest are going to be the same. This is just what is different. So at this carbon, just the way you can see, there will be an H here, there will be an OH here. And then there will be OH here, there will be H here, there will be OH here, there will be H here. The rest are the same. You can count. The formula is C6, H12, O6. Count if the atoms have balanced. Starting with this one, oxygens 1, 2, 3, 4, 5, 6 is there. You can also count the number of hydrogens and the number of carbons. And then also in the other one, oxygens 1, 2, 3, 4, 5, 6, this one here. So they are all the same. Now, when you look at where the oxygens are more concentrated, you can see that there are more oxygens or there are more hydroxides on the what? On the right. So this is called D glucose. Same with this one, there are more OHs on the right. So this is also called D fructose. So if I swap the directions, this one goes the other side, 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 that will become L glucose. And so I'll also swap the direction of these, that will become now L fructose. So that's how you name. So now when you start giving them the names such as L and D, that is what leads to what is called optical isomers. Okay, I'm going to talk about changing the direction when you start looking at each one of them. So hope we have gotten the difference between fructose and galactose. When the functional group is on the middle, that is called a ketone. When the functional group is at the end of the chain, that's an aldehyde. Therefore, glucose is an aldehyde, fructose is a ketone. Galactose is also an aldehyde, so keep that in mind. Now let's look at glucose more in detail. I've not talked about stereoisomers, don't worry, we'll talk about that. So starting with glucose. So glucose, which is also called grape sugar, is a simple monosaccharide which is found in plants. It is important product of photosynthesis, that process when plants, of course, water gets to combine with carbon dioxide, that leads to the formation of glucose. Okay. Now, one thing, you need to understand really the structure for glucose. So just like how just from writing it, well, please, you need to understand this one well, because the way they try to phrase questions, they will give you the structure, they ask you to identify them, so you need to know them. Now, glucose is soluble in water because it has got a lot of OHs. This is one property of glucose. It can dissolve in water because these OHs, remember the first topic that we did, that was atomic structure. We looked at hydrogen bonds. So glucose can form hydrogen bonds with water. Because of that, they're going to interact and glucose is going to dissolve in water. Okay, so let's write the structure. The formula, of course, C6, H12, O6. The way you can write it, if you want, you can show the atoms. Carbon number 1, there should be 6 carbons. Number 2, number 3, number 4, number 5, and number 6. Now this is too much. Let me reduce. 1 there, 2, 3, 4, 5, and 6. So the first thing, please, I'm going to write again because we have got 2 of them. 1, 2, 3, 4, 5, 6. Okay. So the first thing, you need to know that glucose is an aldehyde, meaning that the functional group will be at the end. Functional group is at the end of the chain. Now, one thing, each carbon is supposed to have 4 bonds. If you can see, these are only 2 bonds, 3. So the next bond, it is an hydrogen that is going to come and attach. And then on this carbon number 1, I'm going to put an OH here. This is carbon number 2. And then carbon number 3, I'm also going to put an OH there. Carbon number 4, I'll put an OH there. And then carbon number 5, I'll also put an OH there. For carbon number 6, it doesn't matter the direction of the OH and these other things. So we're going to have OH, H, and then H. And then we're going to have an H everywhere where it's missing, like that. So same with this one, I'm going to put like that. But for this one, I'm going to change directions. Instead of having the OH this side, I'm going to have the OH here. And then I'm going to have the OH here. I'm going to have the OH here. And also the OH here. This one, we can have the OH there. And then the H there, H there. Remember, we are supposed to only use 6 oxygens, so don't exceed the number of oxygens. So these are the two types of glucose. Now if you look at this one, most of the OHs are concentrated on the right. So this is what we call D glucose. This one, the OHs are more concentrated on the left. This is what we call L glucose. Now the most abundant type of a carbohydrate is the D form. This is the most abundant. And so even when we are forming the ring structures, we are going to see them very soon. It's only the D glucose that forms ring structures. L doesn't form any ring structure. Okay, hope we've gotten that. So when you talk about L glucose and D glucose, these are what we call optical isomers. What do we mean by optical isomers? Meaning they turn plane polarized light either to the left or to the right. So this has to do with the turning of light. If light passes through a solution that has got L glucose, it's going to be turned to the left. If it passes through a solution that contains D glucose, it's going to be turned to the right, like that. So that's how this gets to differ. Hope we've gotten that. Now, I can write this same structure you are seeing in skeletal form, and most you are going to find them in skeletal form instead of them being written like this. The skeletal form, we just write a line. We're going to put at the end there the OH and then the H. And then carbon number 2, you can see here, I'm going to put it here. There is OH here, there is H here. Carbon number 3, there is H here, there is OH there. Carbon number 4, there is OH here, there is H here. Then carbon number 5, there's also OH here, there's H here. Carbon number 6, I'm not going to write it like this. I'll just say CH2OH. How is that? This is the carbon you are seeing. And then the two hydrogens, this one and this one, these are the ones you are seeing as H2. And then this OH, that's the one you can see there. So that's how we write the structure for glucose. And this is D glucose, skeletal form. Please, if you want to tell if it is glucose, you should make an S like this. If you just see the structure, if it makes this S, then that's the D glucose. But if the S will be like this, that will be L glucose. Okay, we've talked about optical isomers and also structural isomers. Now, let's see how stereoisomers are formed. So I'm using, remember we are saying only the D form is going to form a ring. Now, because these have got a lot of carbons, they are mostly unstable. Like 6 carbons, they can't be in a line like that, they're unstable. So we're going to see them not as straight chains but in ring form. That's how they exist. 1, 2, 3, 4, 5. First carbon, second, third, fourth, fifth, the sixth. I'll just put CH2 or H. And let me state it again, it's only the D form that is going to form ring structures. Alright. Okay, so this is D glucose. Now, please pay attention to how the structure is going to be formed. So what happens is the anomeric carbon, that is the carbon containing the functional group, is going to react with the second from last carbon. Now, this carbohydrate here has got 6 carbons. So when we're saying second from last carbon, that is the fifth carbon. It is different from pentoses. It is the fourth carbon that reacts with the anomeric carbon. Okay, take note of that. So the anomeric carbon, that is the carbon that is contained in the functional group, is going to react with the second from last, second from last carbon, which is the fifth carbon here. And how is that going to happen? So you are going to see this H of the OH of carbon number 5 is going to go and interact with carbon number 1, and it will interact with this O, which is here. That is going to form an OH, and that OH is what is going to determine what will be the name of that carbohydrate. Now, don't worry. Let's see how it's going to be formed. So this, because there are 6 carbons, it's going to form a 6-membered ring. And that 6-membered ring will look like this. We're going to have an O here, which is the oxygen that remains here. That's the O you are seeing there. Then we're going to have it like that. It's more like a hexagon. Okay, like that. Now, remember, where is carbon number 1? Carbon number 1 is here. On carbon number 1, we have got an hydrogen that has remained there. So that hydrogen can either be on top or down. Let me put it first down. I'm going to also draw another one because the ring structure can also be in two forms. So the H can also be on top. Which H? This H that has remained here. Now, when this hydrogen reacts with this oxygen, they are going to form an OH. That OH can either be on top or down. Now, the position of this hydroxide is what leads to what we call stereoisomers. So stereoisomers are simply isomers that have got the same structural formula, but they've got different arrangement of atoms in space. So this one, the atoms are on top in space, whilst here the atoms are down in space, but it's all the same. So those are what we call stereoisomers. So when the OH is on top, we call that as a beta glucose. So this is going to be called beta. It is coming from D glucose, so that will be beta D glucose. And then the other one you are seeing here is going to be called alpha D glucose when the OH is down. Hope we can remember that. We need to know that. Now, when you see a 6-membered ring, a ring that looks like an hexagon, we call that as a pyranose ring. But a ring that looks like a pentagon in case of hexoses, and also there is in case of pentoses, there is also one hexose that also has a ring like this one. So a ring like this one, we call it a furanose ring. A ring like this one we are seeing here is called a pyranose. So therefore, this one, the first one I've written, can also be called as beta D glucopyranose. But I'll not finish the word glucose, I'll just say glucopyranose. And then the other one, we're going to call it alpha D, that is glucopyranose. Okay, those can also be the names. Now, when you go to carbon number 2, so this is going to be carbon number 2, number 3, number 4 is going to be here, number 5 is going to be there. Same with the other one that side. So when we come on the carbon number 2, this is also carbon number 2. So this ring is going to turn in this way. So these things we are saying here, these are the ones which are going to be outside here. So take note of that also. So at carbon number 2, we are going to have the OH down. and then the H is going to be inside. Carbon number 3, you see we are going to have an H down, and then the OH is going to be inside. Carbon number 4 here, okay, we have the OH down. Actually, this one, the way I put it also is not even that true. So we said D glucose is supposed to have the OH here, 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 and also here. So this is an hydrogen. Hope we took note of that. It's just wrong on the drawing. Okay, like that. So at carbon number 4, this is number 2, number 3, number 4 is here. At carbon number 4, the OH is supposed to be down. And please take note, this is one thing that differentiates glucose from galactose. Because when you're talking about galactose, this OH is going to be on top. So please let's pay attention to that. And then the H is going to be on top. The structure for glucose and galactose are all the same. They only differ at this very carbon, which is the carbon number 4. When you see the OH on top, just know that that's galactose. If it is down, that's glucose. The rest are the same. That's why we say they are structural. They are galactose and glucose. Those are stereoisomers because they only differ the arrangement of atoms at this point. One can be on top, one can be down. If they say examples of stereoisomers, we have got glucose and galactose. We have also beta glucose and the alpha glucose. They are also stereoisomers because for them the arrangement of atoms is different at carbon number 1. Glucose and galactose, the arrangement of atoms is different at carbon number 4. Hope we've gotten that. Now at carbon number 5, we see there's an hydrogen that has remained here. This hydrogen is going to be here. And then we have got this group that has remained. This is going to be carbon number 6. And this one we're going to see it here, CH2OH. So this is the structure for glucose. Same, everything that we are seeing will all be the same also for this one. The only thing that differs is just at carbon number 1. You can see one, the OH is on top, the other one, the OH is down. The rest is going to be the same. Okay, so that is going to be the formula. Now we need to know again that glucose is a powerful reducing agent. The reason is simple. The functional group, this OH, is free. That is why it is a reducing agent. What is a reducing agent? A reducing agent is an agent that reduces other substances while itself it gets oxidized. Now, getting reduced means either losing oxygen or gaining hydrogen. So this group here is free to gain an hydrogen. That is reduction. You can see because it has got this double bond. If you break this double bond, it becomes only a single bond. Then carbon wants to have 4 bonds. That other bond, it needs to be filled by an hydrogen. So glucose is a powerful reducing agent because it has got an aldehyde functional group. Anything that has got a ketone functional group is not a powerful reducing agent. So we are saying reduction, take note, reduction is the loss of oxygen or gain of hydrogen. And then oxidation is going to be the other way around. Let me just write that in case you forget. It is one thing that is very important. Alright, oxidation and reduction is simply the opposite. When you're talking about oxidation, oxidation firstly is the gain of oxygen or loss of hydrogen. You can also explain it in terms of atoms. Oxidation is also, electrons. It's a loss of electrons. So when you want to talk about reduction, it's simply the opposite of this. Reduction is loss of oxygen, gain of hydrogen, and gain of electrons. Okay, now that you've understood glucose, let's look at galactose. Galactose, the formula is the same as that of glucose, C6H12O6. And just the way we wrote the formula for glucose, I'm just going to write D galactose. The L will just be the opposite. Carbon number 1, we have got OH. Then we've got carbon number 2, number 3, number 4, number 5, number 6. We're going to have CH2OH. Now, just like glucose started, we have got OH, carbon number 2, carbon number 3H, carbon number 4 I'm going to skip, carbon number 5 also have OH, H, OH, and then H. So you see it's all the same. For glucose, this was OH and then this was H. So glucose and galactose only differed carbon number 4, in that instead of being like that, this is going to be opposite. We are going to have an H this side and then an OH. This is the only difference between glucose and galactose. For galactose, it's going to make more like a C. The OH is make like a C. For glucose, it makes an S. Hope we take note of that. So the formation also of a ring in galactose, second from last carbon, which is the carbon number 5, the H is going to interact with you know that these are exam questions. They're going to ask which hydrogen of which carbon interacts with the oxygen of carbon number 1 to form the OH, which can either be on top or down in the ring structure. So that is going to interact with the oxygen of carbon number 1. And what we are going to see, we are going to also form two structures. There's OH there. I'm also going to write another one. So the H and the OH, I mean the H and the O, when they interact, they form an OH. That OH can either be on top or down. And depending with where it is, whether it is on top or it is down, that tells whether it is going to be alpha or D. Remember, this one we have used here is D galactose. It's only the D which forms a ring. When the OH is on top, that is got beta. This is beta D. Now this is galactose, but remember it is looking like a hexagon, so we're going to say galactopyranose. It's pyranose because the structure is looking like an hexagon. And then this is going to be alpha D galactopyranose. Okay, so this OH is going to come down on carbon number 2, and then the H is going to be on top. Carbon number 3, we have got an H. This H is going to be down. The OH is going to be on top. Carbon number 4, this H is going to be down. You see the difference. For glucose, the OH was down, but here the H is the one which is down, and then the OH is on top. And then here, this H which remained is going to be down. And then this group which you are seeing here is going to be on top. So everything is all the same. So everything else is the same in alpha and D, apart from carbon number 1. Yes, Jacob.
Drawing when you're putting carbon, how do you know that this hydrogen is supposed to be on top or this one is supposed to be down?
Okay, so the way this structure is, you are turning it like this. You are turning it in this way. So everything that is this side is what will be down. Does that make sense?
Yeah, it's clear now.
Okay. So this is galactose.
If you can just repeat that point.
All right. So everything, when you are forming a ring structure, we're going to turn this one in this way. Everything that you can see on the right hand side is what will be appearing, apart from carbon number 1. Forget about carbon number 1 because it's a combination of this hydrogen and carbon number 5 with the oxygen and carbon number 1. But carbon number 2 up to carbon number 2, number 3, number 4, those things which are on the right, those are the ones which you are seeing down there. Is it okay now? Okay, so just like glucose, galactose is also a powerful reducing agent. Galactose is also a powerful reducing agent. It is also it forms a pyranose ring, which is only different from glucose at carbon number 4, which is this point which is here. So for glucose, the OH is above the plane. In galactose, the OH is above the plane, while in glucose it is below the plane. When glucose and galactose combine, they are going to form lactose, which is called milk sugar. The milk sugar or milk. All right. Now let's look at the structure for fructose, which is the last disaccharide. The formula is the same, C6H12O6. But remember, galactose and glucose, those are aldehydes, meaning the function groups are at the end of the chain. But for fructose, fructose is a ketone because the function group is on the middle of the chain. The function group actually is at carbon number 2. So carbon number 1, C2, CH2OH, even the last one, C2, CH2OH, and then we're going to have 4 more carbons here. Carbon number 2, number 3, number 4, number 5. So just, it's all the same as I drew earlier. It's all the same like in glucose. You are supposed also to make more like an S. But remember, at carbon number 2, you are supposed to have the functional group. So this is where we're going to have a double bond with the oxygen, carbon number 2. You don't need to have any other atom because there are already 4 bonds. 1 bond here, 2, 3, 4 bonds. So the carbon is already bonded to 4 things. Can't be bonded to anything more than that. And you're supposed to form an S. If it was glucose, this was supposed to be OH, and then H, OH, OH. But this is no longer an OH. So this is going to be H, OH, OH, just like a glucose. This is going to be H, it's going to be H, this is going to be OH. Okay, like that. It's always the D which forms this structure. So this one I'll put here is D fructose. Now again, the second from last carbon, in this case carbon number 5, is going to react with the anomeric carbon. Now in this case, the anomeric carbon, or the carbon containing the functional group, is not at the end of the chain, it's carbon number 2. So this hydrogen you can see here is going to interact with the oxygen, which is at carbon number 2. That is where the anomeric carbon is, like that. Now this is going to form not a pyranose ring. Even if it is a hexo sugar, it doesn't form a pyranose ring. It is going to form a furanose ring. So the ring it forms looks more like for those for pentoses. I mean, yeah, pentoses. This is how it's going to look. So I'm going to put 2 of them because we've got alpha and beta. Okay, like that. So when this H O and this H react, they are going to form an OH. the OH can either be above or below at carbon number 1. Now here it is not the hydrogen or the oxygen that is going to be on top or down. This group you are seeing here is the one which is going to either be on top or down. So here we're going to have the CH2OH on top, even here CH2OH here. So in this case, this is not carbon number 1. Carbon number 1 is here. This is going to be carbon number 2. This is number 3. This is number 4. This is number 5. The number 6 is going to be this one, which is here. So same also here. The number 6 is going to be that group. But for that one, there is an hydrogen that has remained here. The hydrogen is going to be down here. It's also going to be down here. Now you see these more look the same. So to tell which one is carbon number 1, you just see where there is an OH. That will be the carbon number 1. So if they asked which one between this one and this one, which one is carbon number 1? Carbon number 1 should have an OH. That's the difference. Okay, from here, carbon number 2 is this one. We have already filled it. And then we go to carbon number 3. That means this H is going to be the one which is going to be below. And then on top we're going to have OH. And then inside, this is going to be below. That is going to be down here. And then we're going to have an H. This is fruct. Also here it's all the same. H, OH, and then also here OH, and then H. So the first one you can see here, because the OH is below. Whenever you see that the OH is below, that is always the alpha. So this is going to be alpha D. This is fructose. I can say fructose, but because this is a furanose ring, I'm going to say fructose. And then this is to beta D, fructofuranose. So fructose is the only hexose sugar that is a furanose. The rest are paranose. Now, because fructose has got the functional group at carbon number 2, it is not a strong, it's not much a strong reducing agent. It is a weak reducing sugar because it's open chain form. This is what we call the open chain form. This is the ring chain form. Its open chain form is a ketone. That is why it is what? It is it's a weak reducing sugar. Okay. So carbon number 2 of fructose is asymmetric, leading to the formation of alpha and beta. What do we mean by asymmetric? Asymmetric, the other word we can use is chiral, meaning it is bonded to 4 different things. So if you can check, you are talking about not in this structure. In this structure, carbon number 2 is not asymmetric. We are talking about the ring structure. 2 is here. It is bonded to 4 different things. 1, 2, 3, 3 portion this thing which is this side, and then 4 this thing which is this side. So that is why we are saying carbon number 2 is asymmetric or chiral in the ring structure. And again, fructose is a structural isomer for glucose. Remember that. So this is about the monosaccharides. And the next time now we're going to look at the disaccharides. This is all about monosaccharides.